Hello! This is section 2.2 on inverse variation. Here's your journal choice. I think you are going to enjoy this section a lot. So let's go ahead and jump in here. Okay, objective and what's the point? It's very similar to the previous lesson. This is another type of relationship. It's just a little bit different than direct variation, and the reason we do this is to make predictions and figure out what data is going to do in the real world. Okay, inverse variation. An inverse variation equation is an equation where one variable gets big, the other one gets small. So this relationship is similar to direct variation because they're both going to go up at the same speed, but in direct variation both get big or both get small. In inverse variation, if one is getting larger, the other is getting smaller. So these are doing the opposite of each other's, which inverse. We say one quantity varies inversely as the other or is inversely proportional to. So the key words we're looking for today in any word problems is varies inversely as or is inversely proportional to. And this whole lesson is going to be almost identical, like I said to yesterday, except really we're just using a different equation because it's a different relationship. Okay, here is the function. When we read those key words, inversely proportional to, we are going to write this function down. Y equals k over x to the n. Okay, again, k can't be 0 because if that's the case, we just had y equals 0 and there's no real relationship there, and n has to be positive. These are all examples of inverse variation functions. T equals 48 over w. Y equals k over x, in this case to the first power. K is 48, the constant of variation. Obviously this one is y equals k over x to the first power. That's very similar to what we just had here. D equals k over w, another example. I equals k over d squared. Y equals k over x squared. K is called the constant of variation just like it was yesterday. That has not changed. Okay, steps to solving are nearly identical like I have said multiple times so far. Again, all we're going to do is change that first step to when you read the words, you're not going to write y equals kx to the n, we're going to write k over x to the n. So if you wrote out those steps yesterday, the only thing you'll change is that formula that we're going to use when we read inversely proportional to, we will write this down instead. Okay. The number of units u in a length varies inversely with the length of the unit. Write an equation that expresses this relationship. As soon as we read the words inversely, varies inversely, you should write this general form down. This is the general form. After you've wrote that down, general, then you will fill in the variables that they give you. U varies inversely, so u is on this side because u is going to be the dependent, the equivalent to y, and L is your independent. There is no exponent in this example because it doesn't say the square of L, it just says the length L. Alright. This is kind of interesting to me. The law of the lever, I don't know, I call it a teeter-totter. Some people might call it a seesaw, but I think teeter-totter is more fun to say, so that's what I'm going to say. I bet you all have memories of the teeter-totter, and you probably have some horrible memories. I know I do. We used to have a teeter-totter whenever I was in elementary school, and it was a very sad day when I was sitting on the top and somebody jumped off and I bit my tongue and I cried. That may have been the last time I was on a teeter-totter. I have some emotional scars from that. But I think all kids realize that if somebody is heavier than they are, that it's helpful. Sometimes they used to sit in front of the handles to balance it out. Okay, that's because to balance a teeter-totter, you need to have some sort of relationship with your weight and the distance from the pivot. Okay, this is a formula. If you see a teeter-totter question on your homework, you're going to be applying this formula, D equals K over W. If it was a test or quiz, I would give it to you, or it would be given in the test. You don't need to memorize it. But here's a relationship. The distance from the pivot, which is called the fulcrum, in meters, so we're talking meters here. This is the distance. The weight of a person in kilograms, and K is your constant. So distance equals the constant, which we're going to figure out, over the weight. The reason this relationship works is because D times W on one side has to equal D times W on the other side. So if this person gets heavier, this distance has to be less, and so on, to keep it balanced, okay? So let's look at an example. D equals K over W. I'm going to write that down. Using the seesaw example. In example 2, suppose Carrie weighs 34 kilograms and is 1.8 meters from the pivot. If Madison weighs 38 kilograms, how far from the pivot should she sit? Okay, so we know it's an inverse relationship, and yes, it does not say so explicitly in the problem, but we know it from experience with the formula. So we're going to go ahead and use this formula we're given. The data that matches that we're going to plug in to figure out K is the 34 kilograms and the 1.8 meters. So I have 1.8 meters equals K over 34. How do you get K by itself? Well, you multiply both sides by 34, and you get K equals, I wrote this down, 61.2. And I forgot to give you guys the answer on this before we went, so sorry about that one, but I'll do it on the next problem. So now I have D equals 61.2 over W. Okay, and now this formula can figure out how far anybody needs to sit as long as they know how far they weigh when they teeter-totter with Carrie. If Madison was the one we figured first, she would have a different K value. So we'd have to figure out for each person. But Madison weighs 38 kilograms, so I have D equals 61.2 still over 38. We go ahead and divide that out, and we should get the answer, which I forgot to show you, sorry, of 1.6 meters from the pivot. Okay, that was a fun problem. I like to teeter-totter. Okay, inverse square relationships. We see these a lot in the real world. It has a lot to do with light and sound intensity, which obviously we deal with light and sound a lot in life. So it is an inverse square relationship. We call it that because it's inverse because of the y equals k over x, and then the independent variable is squared. Here's a formula we will use frequently, I equals k over d squared. You don't have to memorize it, but you might want to have it handy in your notes in case it comes up on a homework problem. This is intensity in lumens. You can read distance from source in meters. Okay, in example 3, this is from your textbook. Suppose the intensity of light 6 meters from a light source is 30 lumens. Find the constant of variation and determine the intensity of the same light 9 meters from its light source. Okay. Go ahead and work this now if you'd like, and then check your answer. Here's the answer, 13.3 lumens, which we could round to 13 lumens. Okay, I will now do the work, so if you got it right, you can go on from here. If not, you're going to come along for the ride while I do this. Suppose the intensity of light 6 meters is 30 lumens. So we're going to plug things in here. That is the matching data set. 30 for intensity equals k over 6 squared. Do the 6 squared first. 30 equals k over 36. Get k by itself. Multiply both sides by 36. And I get k is 1080. Okay, I'm not done yet. That is just the k value. You take the k and you plug it back in to this problem. Actually, it didn't go up high enough. This problem. I now have I equals 1080 over d squared. They're asking what it would be if it was 9 meters from its source. So I'm going to plug 9 in here for d. I equals 1080 over 9 squared. We know 9 squared is 81. I is 1080 over 81. And we get, ta-da! 13.3 repeating bars. We should probably round. I don't know how they report lumens because I don't have a lot of experience with it. Someone in electricity might be able to tell me. So I don't know what the rounding procedure is on that. So we'll just leave it as it is. Okay, next problem. Is it inverse variation or not? Here's a good thing to ask. If one is getting large, is the other quantity getting small? If one is halved, will the other double? These are things you can ask yourself to check. Okay, So let's look here. The rent R of an apartment is split evenly among n people. As the rent goes up, will the number of people go down? I don't think so. This does not make a lot of sense because the word evenly. So the more people, well, I guess if they're talking rent each person pays, the more people there are, the less each person pays. So if that's the case, yes. But if I think the rent would be constant of an apartment, if they're talking about that, and the number of people, then it wouldn't be. This one's kind of a wishy-washy one. Let's talk about that tomorrow in class because I want to see what your guys' take of that is. The rent R of an apartment is split evenly among m people. I think it all determines what you read R to be, if you said R was what each person paid or if R was the constant value of the rent. So we can talk about that one tomorrow. The distance D you travel in a car if you are going at a constant speed S. Okay? Constant speed S. So, again, this is going to stay constant. So if the speed goes up, will the distance go down? No. If the speed goes up, you'll go farther. So that is definitely not. The time t it will take to get to a destination if you travel at a rate of r, okay? If I go faster, will it take less time? Yes, one's going up, this one's going down. That is a yes. And this one is tricky. The distance d between n evenly spaced buttons from the top to bottom of a particular shirt. Hint, draw a picture. An inverse square relationship when one is doubled, the other is divided by 4. Okay, here we go. Here's my shirt. Oh yes, that is really amazingly good. It's okay if you're not as good as me. Just remember, one day you can be as good as Mrs. Bruno. Okay, they're asking if I get more distance. So if the distance gets bigger, those are pretty far spaced. There's less buttons. If the distance is less, oh, that one wasn't as good. There are more buttons. You guys see that? So, more space, less buttons. Less space, more buttons. This is inverse variation. And what I was saying by here, if one is doubled, is the other half. If it's inverse square, if one is doubled, the other is actually divided by 4. We'll talk about that more later. This chapter. So it doesn't have to go up the exact same increments because if it was inverse square, one would be growing a little faster while one was shrinking a little slower. But we'll talk about that later this chapter. Okay, that's all I have for you. If you would, please read over the activity in 2-3 because we are going to go over that in class tomorrow. And have a good evening. See ya.